Hello, everybody. Welcome to the July 11th The Nutritionist. I am Marianne Fessenden from AMTS. Our webinar this month will be offered for listening twice at 9 a.m. and 6 p.m. Eastern Daylight Time. Questions will only be answered in the morning session. The afternoon session will contain a recording of the morning question and answer session. I am delighted to have with me our 2019 co-hosts. I am joined by Paula Torillo from Afina in Argentina, Elena Bonfante of Dairy Innovations Italia in Italy, Vadim Bakchavnikov of Novolab, Russia, Sean Lee of Ansai Tech, China, and Marcelo Ramos from 3R Lab in Brazil. In the morning, depending on how you are listening, you can submit queries through me or one of my attending co-hosts. Later, a complete recording of archived webinars as well as a question and answer session for each will be available on the AMTS website. For those of you who would listen to the presentation whilst driving, we have converted the videos to MP3 files that can be downloaded to your device for offline listening. These podcasts can be found at the Ag Model Systems website under the Webinar tab or Resources tab. This month, we are very pleased to host Dr. Geoff Dahl, the Harriet B. Weeks Professor in the Department of Animal Science at the University of Florida, Gainesville. Dr. Dahl conducts applied and basic research with direct impact on dairy production. Specific research interests include effects of photoperiod manipulation on production and health, and the impact of frequent milking and early lactation on milk production, and heat stress abatement during the dry period on cow and calf productivity and health. Geoff is working in Bari, Italy this summer. It is likely giving him new appreciation of heat stress, but perhaps living in Florida in the U.S. really does that already. Because he is several hours ahead of us, we are unable to have a question and answer period in the evening webinar. So at this point, enjoy the presentation, and for those of you who listen in the morning, ready your questions. They can be keyed into the chat or the Q&A sections in your webinar app. For those of you listening in the afternoon webinars, this is all pre-recorded. You will hear the morning questions, but you won't have an opportunity to ask questions. You may send questions to me at marianne@agmodelsystems.com or webinars@agmodelsystems.com, and I will forward those questions on to Dr. Dahl. So thank you, and once again, get ready to listen to Dr. Dahl.
Okay, thanks, Marianne. And now we're going to talk about dry period heat stress and the effects on the cow in the next lactation and also on the developing fetus. Because there are influences on both of those animals to program them for poorer productivity. So everyone's well aware of the effects of heat stress during lactation. If we have a cow that experiences heat stress, she's going to decrease her dry matter intake. There is a reduction in milk yield, but that milk yield reduction is actually more than we'd expect given the dry matter intake reduction, because she has to use additional energy to get rid of that excess heat. So she becomes even less efficient than we would expect her to, just given the drop in dry matter intake. And it's been looked at that the recovery on those animals in terms of going back to where they would have expected to have been on the lactation curve is going to depend on how long they actually experience heat stress. So the longer they experience heat stress, the less likely they are to get back to where we would have expected them to be on the lactation curve. A lot of the work that I've done really over the last 20 plus years is focused on interventions that we can do with dry cows in order to improve those animals' performance as they go through the transition into lactation. And so we had the question, what would happen if cows that were dry were heat stressed, and what were the implications of that heat stress? So what we're going to cover for the rest of the time here is kind of split into two areas. The first idea is to look at the effects of heat stress during late gestation, so during the dry period, on the cow in that next lactation. We're going to look at milk yield effects once she calves. We're going to look at metabolic effects both before she calves and also after she calves. And we're also going to look at immune function in those animals during the dry period when the heat stress is actually imposed and after the animals calve in, because there are some lingering effects on immune function in those animals as well. And then we'll talk about the other half of the equation, which is that developing fetus. So those calves that are in that mom that's heat stressed are also heat stressed. And they have a little less ability even to deal with it than mom might. So we're going to talk about what happens when those calves are heat stressed during the final stages of development on early life events like calf health and calf growth. And then we'll talk about heifer growth and reproduction. And finally, we'll cover the impacts on those calves when they come into the production string 2 years later, because there are some influences of that early life or the actually late term effects during gestation on that animal 2 years later. So one of the reasons that we got interested in this area was really this very simple analysis. What we did was looked at the total average monthly production of cows in Florida over a 4-year period, just graphed it out by month. You can see that there's a very consistent seasonal response, with the high in milk yield occurring typically in March or April, and the lows in milk yield occurring in September, October. And then against that, we graph the average high temperature in Florida. And again, that's going to have a very consistent annual cycle, sort of the inverse of the milk production cycle, where we have our low temperatures in January and December, and our high temperatures in June and July. But what you first observe when you look at those curves is that they're offset a little bit, so they're not aligned. The low milk production actually occurs when we're actually seeing a decrease in the average high temperature. So we have an offset of about 2 months with the high temperature and the milk production. So if all the effects of heat stress were just on lactating cows, then we would expect it to be aligned. So the high temperatures would be at the same time that we have our lowest milk production, but we don't. There's an offset, so it appears that there's more going on in terms of heat stress, and we think obviously it's in dry cows, and that dry period influence, particularly in those animals in the summer, is limiting their milk production through the fall. So just to give you a little bit more information on how we've done the studies that I'll present today, this is a photo of our barn at the University of Florida. You can see it's open-sided, but it is obviously shade providing. It's a double 4 row stall arrangement, and we have fans over the sand-bedded free stalls, and then we have soakers over the feed line. Those fans are going to come on at 21 degrees, and the soakers come on for 1.5 minutes every 5 minutes once we hit 22 degrees. So those animals are going to have access to active cooling. And our lactating cows, we're going to have access to active cooling year-round pretty much. And this just shows the effects of our environment, even in that barn, on temperature and humidity. So all we're showing here are the 2 treatment groups from one of our studies. And the point to be made is that really our environment leads to heat stress. The average temperature is lowest in the morning. It's going to be around 23 degrees Celsius, so 73, 74 degrees Fahrenheit. And we see that we peak in the afternoon typically, and this is in summer temperatures, and we're going to have 90 plus degrees Fahrenheit in those animals. But the real killer for us is the humidity. You can see that in the morning when we have those relatively low temperatures, we're essentially at 100% saturation of the air in terms of moisture. So it's very hard for animals to get rid of excess heat under those conditions. And even in the afternoon when we have somewhat lower relative humidity of 60 to 65%, that's going to correspond to the average high temperatures. So our animals, if they don't have access to active cooling, are really going to struggle to maintain a normal rectal temperature. And that's in fact what we see. Even in a shaded environment, those animals need active cooling in order to keep their temperatures normal. So in our barn, if we have remove the fans and the soakers, which is how we implement our heat stress treatment, we're going to see a rise in rectal temperature in animals. So shown here in the open symbols are the animal's rectal temperature in the morning. It's going to be higher in the heat stress, and certainly in the afternoon, it's going to be significantly higher. And throughout most of our studies, if we look at an average response, it's going to be about 0.4 to 0.5 of a degree Celsius rise in temperature, which may not sound like a lot, but you have to remember that in our studies, the animals are going to be experiencing that heat stress for the entire dry period. And just a note on our dry period, we're using for our studies all mature cows, so they're second lactation or greater, and we target about a 6-week dry period in those animals, so roughly 42 to 45 days. So that means that under these conditions of heat stress, the animals are going to have that elevated temperature for a good 6 weeks straight. And when they have that for the dry period, this is what happens to milk in the next lactation. So we've just shown data from one of our studies looking at essentially the entire lactation. And you can see that the solid squares are indicating the animals that were cooled when they were dry, and those contrast to the open circles that they're animals that were heat stressed when they were dry. So there's an immediate effect on milk yield. You can see that it persists for the entire lactation. After the animals calve, they're all under cooling conditions, so they're all exposed to fans and soakers. They're all going to be in the same barn, in the same pen. They're milked at the same time. They're all fed the same diet. So there's really nothing during lactation that would explain these differences. The only thing that we've done differently to the animals is expose them to heat stress or cooled them during the dry period, and that results in this kind of a response. And this is just all the studies that I'm able to find in the literature showing the same effect. So many of these studies are ours, but there are also other labs that have shown the same thing. In every case, if you look at the solid bars, those are the animals that were cooled when they were dry versus the open bars that are the animals that were heat stressed. And in every case, the animals that were cooled make more milk in that next lactation versus the animals that were heat stressed. So a very consistent response across levels of production. Different labs all have the same outcome. So we wanted to know a little bit more about why this was occurring. And if we can think about milk production at the mammary gland level, it's really a pretty simple function of the number of those secretory epithelial cells that there are in the mammary gland and how hard they're working or their metabolic rate. Because this effect that we observe is there from the beginning of lactation and extends for the entire lactation and extends after treatment's been removed, it's much more of a case or likely case that it's going to be an effect on epithelial cell number rather than metabolism. So we wanted to look at that. And again, if you think about it, it's fairly straightforward. We can see more epithelial cells by seeing more proliferation or growth, or we can see slower decline of those cells, so slower loss of those epithelial cells. That would also potentially result in a greater overall number. So either one of these is possible, and we wanted to look at this during the dry period and then again during lactation. So we took a series of mammary biopsies from animals in one of our studies. And what we observed was that proliferation increased in the animals that were cooled relative to those that were heat stressed. So this is at about 3 weeks before the animals were actually due to calve. So given a 6-week dry period, that's about 3 weeks after we dried them off. And I think you can see pretty clearly that the epithelial fraction is much greater in the animals that are cooled versus those animals that are heat stressed. So those are the secretory cells. The stroma, that makes up the sort of supportive tissues in the mammary gland, and even those are increased as well. And overall, then, the total mammary cell proliferation is increased in the cooled cows relative to those animals that are heat stressed. So that's pretty suggestive of an increase in capacity of the mammary gland in that next lactation for milk production. But of course, we wanted to look at cell death to make sure that we weren't netting out no change. And in fact, we weren't. So over on the left of the slide, as you're looking at it, you can see that day minus 20, that same time, this is an indicator of cell death, and there's no difference between those two treatments. So the cooled animals, same rate of cell death as the animals that were heat stressed in the epithelial fraction. Now there's an increase at the time of calving, and there's a lot going on in the mammary gland. We are always going to see some loss of cells at that time, but there wasn't a difference between the treatments again. So even with that increase around the time of calving, there's no difference between the cooled animals and the heat stressed animals. And then further out into lactation, again, no difference in terms of the rate of cell death. So that leaves us with no change in cell death, but an increase in proliferation, suggesting that those cows that are cooled when they're dry are going to have greater capacity for milk yield in that next lactation. So one of the questions that came up from a practical perspective was, how long do I actually have to cool the cows when they're dry in order to observe this response? Would it be possible to just connect this with the close-up phase from a dietary standpoint and a management standpoint? So we looked at that question with our typical model where cows are going to be cooled or heat stressed from the time they're dried off. And so panel A and B here represent the rectal temperatures and the respiration rates in animals that were either cooled at dry off or exposed to heat stress. And you can see in these data, which are the first 3 weeks of the dry period, heat stress increased rectal temperature, and it also increased respiration rate, just like we expected it to. So after about 3 weeks dry, we took half of each of those groups and we put them on the other treatment. So the animals that were in the cooling were maintained. Some of them were maintained in that, and half of them switched over to heat stress. The animals that were in the heat stress, some of them were maintained in heat stress for the rest of the dry period. Some of them went to cooling. So we ended up with 4 groups, and that's what panel C and D represents, is the rectal temperature and the respiration rate from those 4 groups for the last 3 weeks of the dry period. So the cooled animals, whether they were cooled the whole time or transitioned to that from heat stress, lower rectal temperature than the animals that were in the heat stress the whole time or for the last 3 weeks. Same thing with respiration rate. So all this is illustrating is that we got sort of our gross physiological responses that we expected by exposing animals to heat stress. But then we looked at gestation length in the animals and following on from that, dry period length, because we think that there are some influences of placental function on the responses that we're seeing. And that's going to have an impact not only on the cow from a hormonal perspective, but also on that developing fetus. And we'll talk about the calf in a little bit. But just getting a gross estimate of placental function, if we see a drop in the animal's gestation length, it's suggesting that we have some placental dysfunction occurring. And that's in fact what we see. And other folks have seen that as well. Cows that are heat stressed tend to calve in sooner than the animals that are cooled. And we usually see about a 4 or 5 day reduction in gestation length in animals that are heat stressed. What was interesting to us was the animals that were in both of our switch groups also had a reduction in gestation length. They weren't different from the animals that were heat stressed for the entire time, but all 3 groups were significantly less than the animals that were cooled for the entire dry period. So that's suggesting that there is a similar decrease in placental function in animals that are experiencing heat stress either early or late in the dry period. And that probably explains some of the milk responses that we observed. So shown here is milk production. If you look at the open boxes, those are the animals that were cooled for the entire dry period. And the open circles are the animals that were heat stressed for the entire dry period. And just like we've seen previously, there's a significant difference in milk yield in that next lactation, favoring the cows that were actually cooled. The solid symbols represent the 2 groups that were switched. And I think that it's pretty clear to see that there's no difference of those animals from the animals that were heat stressed for the entire dry period. And as expected, well, not as expected, but that those animals then are somewhat lower. They're significantly lower than the animals that were cooled for the entire dry period. So it looks like any heat stress during the dry period is going to have a negative impact ultimately on the animal's productivity in that next lactation. And the real bottom line is we need to get those cows cooled for the entire dry period in order to observe this response. Now, of course, not everything is going to be generated at the mammary gland level. We've got to have some metabolic support for that increase in production or changes in production as well. So in this slide and the next couple, they're kind of set up the same way. The shaded area is when the animals are dry, and the open sort of area of the figure is going to be when the animals were post-calving, so in milk. And just like with lactating cows, when we heat stress cows in the dry period, we see a reduction in dry matter intake. So they are consuming less feed when they're dry, but after they calve in, there's no difference in intake. So one caution here is that when I say there's no difference in intake, we really haven't measured it very far out into lactation. This is only about 6 weeks into lactation, so we haven't gone nearly as far as we have with our estimation of milk yield responses further out in lactation. And certainly at some point those cows have to diverge, because the cows that are cooled previously are making a lot more milk for the rest of that lactation. But the real point here is that there is a reduction in intake during the dry period with heat stress, similar to what we would see in lactating cows exposed to heat stress. And then if we look at body weight responses, they're pretty much as you'd expect as well. On the y-axis, you can see those two symbols there. That's the beginning sort of dry off body weight, and there's no difference between the two groups, but there is a decrease, or at best a maintenance of body weight in the animals that are heat stressed when they're dry. And in contrast, the animals that were cooled actually gain some body weight during the dry period relative to those cows that are heat stressed. After they calve in, though, there's an inversion. So the cows that were cooled when they were dry lose more weight than the animals that were heat stressed when they were dry. Of course, that makes sense with the higher level of milk yield in those cows and no difference in intake. They've got to be getting that energy from somewhere, and it's mobilization of stored reserves that are providing that additional energy to produce more milk. We've also looked at insulin and some of the metabolites in these cows to try and get a little bit better handle on what might be occurring. Again, the shaded area is when the cows are dry, and when the cows, half of them anyway, would have been heat stressed. And the open area is when the animals have calved in. So as you can see, insulin is no different between the two groups. Basal glucose, no different between the two groups. And essentially non-esterified fatty acids aren't different either until we get to parturition, where we see some separation and an increase in the cows that were cooled versus those animals that were heat stressed. Again, not surprising, they're mobilizing tissue reserves to meet that higher energetic demand for higher milk production. But the point is that that is not occurring in response to heat stress. It's really a pull of that higher milk production rather than a direct effect of the heat stress. So this is a little different from some data that you might have observed for animals that are lactating, where we're going to see them move into more of a negative energy balance. And we're going to see shifts in NEFAs and glucose and insulin responsiveness. We don't see those direct effects of heat stress on insulin and metabolites in the dry cow, but again, those animals aren't producing milk, so they don't have that additional energetic draw on them. So that's probably the reason why we don't see as much of a change. So the last area we're going to talk about in the cow is immune function. And so shown here is one of our first studies where we just looked at what's essentially the sort of gold standard of an indicator for immune status. That's white blood cell or lymphocyte proliferation. And we looked at this when the animals were heat stressed, so during the dry period. You can see that proliferation of white blood cells was lower in the animals exposed to heat stress relative to those animals that were cooled. So the animals that were cooled actually, at least from this measure, improved immune status versus the animals that are heat stressed. And then looking at another aspect of acquired immunity, which is the response to an antigen. So animals are going to have an antibody production response to a foreign protein. In this case, we use chicken egg white to induce that response just to get a measure. And we see that there are differences due to heat stress. The animals that were heat stressed actually had a lower response to subsequent boosts with that antigen. Those are shown in the open symbols in the grayed area, and the animals that were cooled, those are the solid symbols. So the cows that were cooled actually had an improved response to an antigen, and that may have some implications for the vaccination protocols that we have cows on during the dry period. So another positive impact of cooling those dry cows may be on immune status. Once the animals calved in, now remember they're all cooled at this time as well, there's no difference in Ig responses to subsequent titers. So we don't know whether that's an effect of lactation or whether that's an effect of cooling, but certainly there's no further effect in those animals. And then if we shift to the innate immune response, these neutrophils are sort of the first immune cells that arrive at an area of inflammation or a problem. We see that there's no real effect during the dry period of heat stress or of cooling. So the animal's oxidative burst, their phagocytosis percentage, no difference between the heat stressed and the cooled animals. What we do observe is a split once the animals have calved in, where the animals that were previously cooled, and remember they're all cooled at this point, but the ones that were previously cooled in the dry period actually have an improved response versus the animals that were heat stressed. So there's a lingering sort of carryover effect on immune status as well, with it being an advantage to have been cooled when they were dry versus the animals that were heat stressed. So it's difficult to get the number of animals that we would need on a controlled study to examine some of the disease and reproductive responses that we want to take a look at, given what we've seen in terms of productivity and immune function. So we had to take a little different approach. And what we did was work with a commercial farm, very consistent high-level management. And we just went in and looked at their records of their dry cows, or their cows that were dry during hot months of the year and cows that were dry during cool months of the year. And in this case, farmers in Florida, they would have had essentially no housing for the animals. They were just out on pasture when they were dry. So the cows had to have their dry period completely contained within the hottest months of the year, June, July, and August, to be in that treatment group. And the other treatment group was cows that had their entire dry period during the cooler months of the year, December, January, and February. So the first thing we looked at was to see if we still had a milk response with this sort of seasonal approach. And in fact, we do about 550 liters more milk in the cows that were dry during the cool months of the year versus those cows that were dry during the hotter months of the year. And there's no difference in genetic potential between the two groups. So that suggests that timing of the dry period is going to have an impact on productivity. We also then looked at a number of diseases in the animals, and what this is showing is if there's a 0, that means they didn't have the disease. If there's a 1, it means they did. And for mastitis, respiratory disease, and retained fetal membranes, all of those were increased in the animals that were dry during the hottest months of the year versus the animals that were dry during the coolest months of the year. The only disease that was a little bit higher in the cows that were dry during the cool months of the year was digestive diseases. And that's going to be in large part probably due to a little increased incidence in ketosis, which would make sense. Those cows are producing more milk, so we're going to have more mobilization of tissue reserves, so they may come up as positive for ketosis. But I'd point out that even in this study where we had that little bit of an increase, that didn't hold them back from producing more milk, and it certainly didn't lead them to have increased incidence of any of the other diseases. So they were able to manage that pretty well. The other area we looked at was reproductive performance. And here we see that the cows that were dry during the cool months actually have improved reproductive performance as well. So the number of breedings to get them pregnant was significantly lower. The days in milk to breeding was lower in those animals. the days in milk to pregnancy then was lower. So all of that adds up to positive effects on reproductive performance. It's also important to point out that the cows that were dry during the cool months of the year that had better reproductive performance actually were producing more milk, and we were trying to get those animals pregnant during the hottest months of the year. So both of those could be acutely negative towards reproductive performance, and yet those animals still showed better reproductive performance. So in terms of the effect on the cow, it's pretty clear, at least from our controlled studies and also from the other ones that we've done in the field, that cows that experience heat stress in late gestation or during the dry period are going to make less milk in that next lactation. Metabolically, they're not affected too much with the exception of that drop in intake when they're dry. But heat stress has direct and carryover effects on immune function in those cows. So when they're experiencing the heat stress, they're going to have a drop in immune function, and then that lingers into the next lactation as well. So nothing really positive at all about heat stress during the dry period. So now let's take a shift and take a look at some of the work that we've done more recently addressing the effects on that developing fetus. As I said, that our target dry period is about 6 weeks. So those calves are going to be experiencing the same heat stress that their dams do for that 6-week period. And as we'll go through, there's some impacts on that calf early in life and as she enters the production strength. So the first effect that we've observed, and again, other folks have observed this previously, so it was not really new data, but it shows just the sort of end result of that shorter gestation length in heat-stressed animals, but also the effects on placental function. So it's really a combination of those two things. The calf is born a few days earlier, so has less time to grow in utero, but we also have a less functional placenta, so we're going to have depression on nutrient uptake as well. And the calves that are born to the cooled animals have a higher birth weight than the animals that are born to heat-stressed dams. What hadn't really been looked at was how long this lasted. And here we show that the calves that are born to the heat-stressed dams continue to lag at weaning. So they're at a lower weight at weaning versus the animals that were born to the cooled dams. And as I'll show you in a couple of slides, we've actually extended this out further in life as well. Perhaps the more important observation that we made was the effect on immune status in these calves. So what we're showing here is the total IgG in circulation. So the Ig that they would have, the immunoglobulins that they would have taken up from the colostrum that they received, are going to be the sort of first immune response for those animals until their own immune system becomes fully activated. And the animals here that are in the solid symbols are those calves that were born to the cooled dams, relative to the open symbols that are the calves that were born to the heat-stressed dams. And it's pretty clear that from day one of life, they have a lower circulating concentration of immunoglobulin when they were heat-stressed in utero versus the animals that were cooled. And what that means then, we didn't have a difference in the colostrum quality, so the percent of IgG in the colostrum. And so the apparent efficiency of absorption, which is that inset graph, is actually reduced in the calves that are born to the heat-stressed dams versus those that were born to the cooled dams. So even though we didn't have a difference in gross colostrum quality, there may be some other factors in colostrum that influence immunoglobulin uptake. And we really couldn't answer that question from this study because in this one, all the animals got colostrum from their own dams. So they would have gotten, if it was a calf that was cooled, it would have been a dam that was cooled, and vice versa. Now we do know they all got the same volume of colostrum. As I said, it was the same quality, and they got it all within the same amount of time after birth, but we really didn't know if there were other factors in colostrum that might be influencing this, or if it was a direct effect on that calf. So we wanted to examine that directly. So we set up another study with 2 experiments. It involved our typical model of heat stress cows for the entire dry period versus cows that were cooled. And their calves then, when they were born, instead of receiving the dam's colostrum, we gave them all colostrum from a large pool of good quality colostrum that we'd created. So they all got the same amount of colostrum. They all got the same amount within the same time after birth, and it was all from high quality colostrum. So what we're really trying to separate out here is any influence of colostrum. Is it an effect on the calf, was really the question of experiment 1. And then the second experiment, we saved the colostrum that those heat stress cows produced, and we saved the colostrum that the cooled cows produced, and we made 2 additional pools. And then we fed that to calves that were born during the cooler time of the year. So essentially under thermoneutral conditions. So no heat stress in utero. So here we're looking at a direct impact on the colostrum, either affecting immunoglobulin uptake or even some aspects of growth in those animals. So the first experiment, remember this is the one where calves were actually cooled or heat stressed in utero and then got the same colostrum. We saw just what we expected in terms of birth weights. So in that panel B, day 0, the calves that were born to heat stress dams are the open bars, and the solid bars are the cooled animals. And there's a difference at birth, there's a difference at weaning, just like we'd shown previously. And we also started to look at gross indicators of the composition of growth. So we're looking at panel A, which is withers height, so how tall those animals were. And you can see that there's a difference here as well, with the calves born to cooled dams being taller at 2 weeks of age and then at weaning again, versus the animals that were born to heat-stressed dams. So that's giving us a little bit of an indication. We've got some other data as well to support this, that there are probably differences in their adaptive responses in utero, such that the calves that are born to heat-stressed dams are going to have changes in their carbohydrate metabolism, probably have a little lower rate of lean growth versus those calves born to cooled dams. Then we looked at the apparent efficiency of immunoglobulin absorption, just like we did in the previous study, and we saw the same type of effect. The calves that were born to the heat stress dams had lower apparent efficiency of Ig absorption relative to those animals that were born to the cooled dams. So that's saying that because those calves all got colostrum from the same source, at least some of the effect is a direct effect on that calf, rather than anything to do with the colostrum that they were receiving. So then we did the second experiment, and this is the one, just to remind you, where calves were all born under thermoneutral conditions, so kind of the cooler time of the year, and then they got colostrum from either heat stress dams or cooled dams. We didn't expect any differences in birth weight. There weren't any differences along the way in terms of their growth early in life, so that colostrum effect was not there in terms of growth responses. And in fact, when we looked at the apparent efficiency of absorption of immunoglobulin, there was no difference between the 2 groups there either. So even though some of the dams had produced it were heat stressed when they were dry, and some of the animals were cooled, that had no effect on the calves' apparent efficiency of immunoglobulin absorption. So it was a direct effect on the calf more so than an influence on colostrum quality or quantity. So in terms of the short-term effects of the calf, we see that cooling during late gestation is going to increase birth weight and weaning weight. There's an improvement in apparent efficiency of immunoglobulin absorption in the calves that are born to cooled dams, but that's not an effect on colostrum quality. That's a direct effect on the calf itself. And as I indicated, we've got some other data that's showing that those calves that are heat stressed in utero are going to have some adaptive responses in terms of their carbohydrate metabolism, going to be consistent with greater fat deposition down the line, so a less productive animal. And that's in fact what I'll show you in a few slides. So we wanted to look at some of these later life effects in these calves. But from any one study, we wouldn't have had the numbers to really look at things like survival in the herd and really look at production responses further out. So we have a very consistent heifer raising program and very consistent management of our calves from birth through weaning and then all the way up to breeding and first calving. So we took records from a series of experiments that we essentially used that same model on over a 4-year span. And all this is showing are the studies that we did with the cows, the responses illustrated in these papers. So that generated about 150 calves total. We looked at some of the early life effects in bulls as well as heifers, but really we were focusing in on our 85 heifers that were born to either cooled dams or heat stress dams, and roughly same number of animals in either treatment group. You will notice there's a little difference in the proportion of bulls and heifers, and that's because we were doing some sex semen IVF work at the same time. All of those treatments were balanced across our heat stress or cooling treatments as well, so they didn't really have any impact on the final result. So in terms of the total data set, we just wanted to confirm that we're seeing the same thing that we see on an annual basis with the smaller numbers, and in fact we do. Calves that are born to cooled dams are going to have a higher birth weight versus those calves that are born to heat stress dams, and bulls are always heavier at birth than heifers are, regardless of whether they're from a heat stress dam or a cooled dam. So we then looked at longer term effects in the heifers. So the animal's birth weight is represented at the left of the figure there, so 0 month of age, and we see our difference there. Weaning differences still persist. The open symbols are the animals that are heat stressed in utero versus those that were cooled. And in fact, that difference persists all the way out to around puberty at 12 months of age, where we still see a significant reduction in body weight in the calves that were born to heat stress dams versus those that were born to cooled dams. So really looking at this sort of long-term effect on body weight gain in those animals through puberty. In terms of the immune status effects on these animals, sort of who survived in the herd or not, here really we want to focus in on is that line that is the heifers that left the herd before puberty due to sickness for the most part. And there we see that there are significantly greater numbers of the calves that were born to the heat stress dams leaving the herd before puberty versus the animals that were born to the cooled dams. And then that, of course, leads to fewer of those calves born to heat stress dams actually making it through their first lactation, and that's the bottom line, versus the calves that were born to the cooled dams. More of them made it through their first lactation. So sort of long-term outcome impact potentially of that early immune status difference. In terms of reproductive performance, we really have sort of small numbers here. That's clear, but just wanted to show some of the responses that we see. There's really no age and difference in the age at first AI between the two groups. The calves that were born to cooled dams, maybe a little improvement in terms of their reproductive efficiency. They got bred maybe a little earlier, probably lost in 1 or 2 pregnancies more in that group because of that earlier breeding. And so it ended up that we didn't really see a difference in the age of calving, but if anything, the calves that were born to the cooled dams have indicators of better reproductive performance than those born to the heat stress dams. And then we looked at milk yield in the first lactation. So this is representing essentially the first 35 weeks of lactation. They didn't come together. We just stopped recording data after we kind of knew what the pattern looked like. The calves that were born to the heat stress dams are in the solid symbol along the top, and the calves that were born 2 years earlier to the heat stress dams are in the open circles on the bottom. And it's about a 9 or 10 pound a day difference in average production across that first lactation. And we've actually increased the numbers of animals that we have in each of these groups since then. And it's just showing the exact same thing. So 2 years earlier, the last 6 weeks of gestation, the calves on the lower line were actually heat stressed in utero, and the calves on the upper line were those that were from the cooled dams. So a significant performance drag in those heifers in their first lactation. So there's no difference in genetic potential between these groups, but as we saw before, there is a difference in body weight between these two groups of animals, at least at a year of age. So we wanted to maybe look at whether these animals that were heat stressed, perhaps in this first lactation, we're going to have some compensatory gain in that first lactation, and that was responsible for this yield drag. Maybe they'd recover in the second lactation or beyond. But when we looked at body weight, we saw that they had already recovered. So these are the body weights in those two groups of animals through that first lactation. And it's pretty clear that both groups calved in at the same body weight. So the calves that had been heat stressed in utero and lighter at a year of age had already compensated. They'd already made up that additional body weight by the time they calved in. And then there was no difference in growth all the way through that first lactation. So sort of that compensatory gain can't explain the difference that we see in milk yield in these animals. And in fact, we've now gone on and looked at what those animals do in the second lactation and third lactation. They don't catch up. And more of a detriment is they actually transmit that to their offspring. So it's a good example of an epigenetic effect where we're not seeing a change in the coding sequence of the DNA, but we are seeing a change in how efficiently that's read across multiple gene pathways. And it results, in this case, of in utero heat stress causing those animals to be less productive for their entire lives. So to sum up the effects on the calf, heat stress in utero doesn't do her any more good than heat stress does to the dam in that next lactation. She's going to be born at a lower body weight. She's going to have lower immune status early in life. Reproductively, she's not as efficient. And more importantly, when she gets into that first lactation, second lactation, and beyond, she's not going to achieve the same levels of production that the calves that were born to the cooled dams did as they went through those same lactations. So we've got epigenetic shifts at play here in the animals that are heat stressed in utero versus those that are cooled. In the dam, it's kind of programming for that next lactation for her to be less productive. But in the calf, it's programming her for life, and she's going to be less productive for her entire time on the farm. So with that, thanks for your attention, and I think we'll turn it over to Marianne to moderate some questions now.
Thank you, Geoff. Thanks for that. I think we're going to have a lot of questions to follow. We have had so many requests to get you to speak over the years that we're glad that you were finally able to join us, even if you were only available for the morning questions. Before we do get to those questions, I want to take care of a few housekeeping details. First, join us next month for Dr. Samuel Fessenden from AMTS. Sam completed his PhD at Cornell University working in the Van Amberg Lab Group. He has been actively involved in the CNCPS model research for over 12 years, having worked on the models starting in his undergrad years. Sam works for AMTS as technical support and European sales. His talk will focus on working in the model for diet formulation and also working with optimization within our program. As with this webinar, there will be two opportunities to join, 9 a.m. Eastern Daylight Time and 6 p.m. Eastern Daylight Time. Now, I would like to thank my co-hosts and the people who helped make this possible. The webinars are organized and produced by AMTS, USA and Global. Our longtime collaborator is Paula Turillo of Afino, which hosts a series as El Webinar del Nutricionista. She receives support from Tecnal, Venus Gladden, and Guillermo Lerman, and RR Lab in Argentina. Marcelo Hens Ramos, AMTS distributor and director of 3R Lab in Brazil, delivers the webinar to our Portuguese-speaking audience. Our AMTS distributor and the director of Ansci Tech, Sean Lee, hosts the Mandarin language webinar platform. We are joined by our AMTS distributors Vadim Bekchevnikov of Novolab in Russia and Elena Bonfante of Dairy Innovations Italia of Italy. We are especially thankful to generous sponsors who make it possible for us to get great speakers and manage the program. We thank our gold sponsor, Arm & Hammer Animal Health, makers of cattle feed ingredients that optimize dairy cow health. Our silver sponsors are Ajinomoto Heartland, superior nutrition through amino acids, makers of AgiPro L, Dairyland Laboratories, Virtus, makers of Strata with EPA, DHA, omega-3s, and Prequel with omega-6s, Dairy One Forage Laboratory, and Jeffo, Life Made Easier. Our bronze sponsors are AminoMax, Purdue Agribusiness, Adiseo, Origination Inc., Nova Meal, Kemin, and PMI. Each of these companies support education and research worldwide. We hope that you consider them in your formulation decisions. I will now open the floor for the morning question period. Again, if it is the afternoon that you're listening to this webinar, there will not be questions to follow. You will be listening to the morning questions. English language listeners, I will read your questions. Remember to type your question in the Q&A tab or in the chat window. Thank you so much, and now we'll go to the live part of the morning presentation. All right, it looks like we'll start with some questions from Paula. Go ahead, Paula.
Yeah. Hi, thank you very much, Dr. Dahl. Okay, the first question is from Javier. Which are the parameters we should measure in the cow or the environment to be sure the cows are not under heat stress?
I think the best thing that you can do is look at respiration rates in the barn. We've just completed an analysis across a few of our studies and linked rectal temperature with respiration rate, and essentially if cows are over 60 on respiration rate, that indicates that they're heat stressed, and the higher that respiration rate goes, the more heat stress they'll be. So I think at the farm level, respiration rate is one of the best ways to determine whether cows are heat stressed or not, and that break point seems to be about 60.
Yes, I have another one. This is from Carlos. He says, it's clear that heat stress reduces dry matter intake, and this increases body mobilization. But from the point of view of the metabolism, do you think the liver is the most affected organ? Some studies show a better response in cows treated with a liver protector, but what do you think about it?
Well, I guess I disagree with the original statement. I think that that's true for lactating cows in terms of them mobilizing more tissue, but at least in our hands, the dry cow doesn't respond quite the same way. So we don't see those shifts in NEFA that we might expect to see in animals that are heat stressed when they're dry versus, back up, Marianne.
Oh, yep.
That we would expect. A couple more. And a couple more, maybe 2 or 3 more slides.
Okay. How's that?
One
Let
more.
me, yeah.
There, right there.
Thanks.
So if you look in the shaded portion here down below, NEFAs really don't change in our cows during the dry period. They change as they hit parturition, but that's not really a direct effect of the heat stress. At least that's not how we interpret it. We think it's more of a direct impact of the higher milk yield in those cows later on. But as opposed to lactating cows that will see shifts in NEFAs and glucose and sort of overall metabolic responses, we don't see that in the dry cow.
Okay. Thank you. I am going to give Paula a chance to do some translations. Elena, do you have questions from the Italian perspective?
Hi. Can you hear me, Marianne?
I can hear you, yes.
Okay. Thank you, Dr. Dahl, for your presentation, and welcome in Italy. I heard that you are here.
I am.
My question was related to the diet perspective in the dry period. So if you know that sometimes the heat stress is very high and probably difficult to handle, most of all in some realities here in Italy. So if you have some suggestion about the diet perspective, if we can do something to help them in order to probably give them, the energy, more energy they need it, to overcome the thermoregulation, or if there is something that can help them also on a nutritional perspective.
Yeah, there's not a lot that we can do, I don't think, from a diet perspective, because that heat is just going to reduce their intake regardless. So the first thing to do is get them cooled off as much as we possibly can in order to maintain that higher level of intake. in terms of feeding fat or manipulating the diet to get it more dense, I just don't think that we're going to be able to overcome the heat effects in order to get more intake into those animals unless we cool the cow. And it also sort of speaks to the point that this lower milk production in the next lactation, I don't believe is due to sort of that reduced intake. Certainly that's a component of it, but I don't think that reduction in intake during the dry period is what's driving this shift in the animal's ability to produce milk in the next lactation. So I would say from a nutritional standpoint, there's not a whole lot we can do to sort of push intake. There may be some additives or other compounds that can sort of help them to maybe maintain a little bit higher level of intake, but I don't think we're going to reverse the effects so much with nutrition.
Yeah, I agree. And another question, if I have to ask, for to the farmer to do an investment on cooling, that can be true for the dry cows, but also for the lactating cow. So would you suggest giving the same amount of money to invest more in fen and plus water, or more fen?
Yeah, I think that you want to do, I think in any time that you're trying to cool cows off, the biggest bang for the buck, so the most efficient way to get to higher levels of cooling is to combine fans with soakers. Doesn't matter the environment, we're going to get, whether it's high humidity or lower humidity, we're going to get better cooling of those cows when we combine water with the fans. Fans alone won't get us cooled cows. It might cause some relief, but it certainly doesn't do nearly as good a job as getting water on those cows as well. So if I had the same amount of money, I'd invest in soakers and fans rather than just more fans.
Elena, if you have more questions, I can come back to you. I have a couple questions. And so, Dr. Dahl, in terms of management recommendations, and given the sort of tremendous success that, at least here in the U.S., farmers have at using sex semen and excess of heifers, would a recommendation be perhaps to consider not keeping those animals that are born and were in gestation during heat stress time, given the lower production and subsequent lactations?
Yeah, obviously that's one conclusion you can draw from these data, that those calves that are born in September, October, pretty much across the U.S., so obviously that's going to be true for Italy. I guess it's going to be true for most of China and Russia, Brazil, and Argentina. We'd have to flip it. So calves that are born, I guess, in March, April, are going to be probably at a lesser capacity, given our data, ultimately for reaching their genetic potential.
Okay. All right. Thanks.
I will have just one more. I remember seeing the graph that was referring to the calves weight, body weight, I think, that actually, or the gain, I don't remember, that was not different from the heat stress mom and the bull.
Yeah. Let me know when I'm getting close.
Yep. So just go up a couple more. No, a couple more. Sorry. There.
Okay.
There it is.
Okay.
Right. So I think you're talking about the inset, Elena, and that was body weight change from birth to weaning. And those were not different. So the body weight change growth, once those calves hit the ground, was not different, but the difference that was there at birth was maintained. So statistically, that body weight change is not different, but they still have differences at weaning. So that would also tie in the birth weight.
Yes, and then we don't have much difference in age at first calving and such, but we see the difference in the milk production, if I recollect well. Correct. right?
That's correct. Yeah, and,
And
and those graphs, like I said, that publication's a bit older now. We have increased the numbers significantly, and they're all showing the same outcome, that in the first lactation, those cows that are born to the heat stress dams don't make as much milk as their counterparts that were born to cooled dams. And in fact, they don't make as much in the second lactation. They don't make as much in the third lactation, and they transfer that on to their offspring.
yeah. And so my question is, do you think it is related with also the programming of the mammary gland? That can, the mammary gland growth and such can be affected also in uterus, for example?
Yeah, we've actually looked at that and have some more recent papers that show that there are differences in mammary structure between the two groups of calves at maturity. It looks like those animals that are heat stressed in utero, that the mammary epithelial cells probably turn over faster once they get into lactation. So we tend to lose cells at a more rapid rate, so that may explain some of their lower productivity.
Okay. No, thank you very much.
Thank you,
Sure.
Elena. I have a couple questions from Paula that she can go ahead and unmute and ask.
Okay, could you make some comments of the effect of heat stress on beef cattle, particularly in feedlots?
Well, I can give you limited information because it's not really something I've worked a whole lot in, so it would just be from reading. But obviously, anytime animals are heat stressed, doesn't matter if they're dairy cow or beef cow, they do see a reduction in intake. I think that in particularly sort of high performance environments, so I'm talking about beef cattle in a feedlot, I'm talking about a dairy cow at the peak of lactation, the bigger issue is going to be the additional energy that she has to use or he has to use to get rid of that heat, which is going to sap performance. So those animals without appropriate shading, cooling, even in a feedlot environment, are going to suffer. And I think that that's pretty well established, that during the summer we do see a drag in terms of days on feed and other estimates that are used to look at efficiency of growth.
And finally, could you make some comments on about the use of additives, some additives to mitigate the heat stress effect?
Yeah, I can only talk specifically about one that we've actually done studies with. We have looked at the impact of Omnigen, and we saw reasonably good responses in animals during the dry period when we supplemented them with Omnigen in terms of, first, their rectal temperature and respiration rate. Although it did go up under heat stress, it didn't go up as much as the animals that were not fed Omnigen. And when they moved into the next lactation, at least for the first part of the lactation, which is all we looked at, their performance was improved with that feeding during the dry period under exposure to heat stress.
Okay, thank you. Paula, Elena, if you don't have any more questions, I don't have any questions in my chat window. Paula says she has no more. I'm going to guess maybe Elena does not. Elena, how are you?
No more.
No more. Okay. All right. Then for that matter, we will close this out. Just thanking you, Dr. Dahl, for joining. And Elena and Paula, always, you are the stalwarts that always attend and ask good questions. Again, thank you everybody for joining us. Dr. Dahl, enjoy Italy.
Okay. Thanks very much, Marianne. Thanks, everyone.
All right. Thank you, everybody.